Good evening, and thank you for joining us this evening at the American Philosophical Society for our November public lecture series. I am not Patrick Spiro. My name is Richard Kagan. I'm an APS member, and I am a professor emeritus of history at the Johns Hopkins University, but since my retirement from that institution in 2013, I've lived in Philadelphia. As many of you know, the society was founded by Benjamin Franklin in 1743 and is today the oldest learned society in the United States. And the APS was founded to, and I quote, to promote useful knowledge, and continues to do so in many, many ways. Its remarkable library, which is just across the street, holds over 14 million pages of manuscripts. The APS maintains a vibrant museum just steps from Independence Hall, and the APS operates the oldest scholarly press in North America. In addition, it provides over 300 research grants a year in all fields of knowledge, but primarily to early career scholars who need, especially now, support most. And above all else, the Society celebrates great scholarship, and that's why we're here this evening. The Society awards a number of prizes that recognize important new scholarly contributions. And one of those prizes is the Patrick Supps Prize in Philosophy. Patrick Supps, who died in 2014, was a leading cultural historian, taught for many years at Stanford, and this award was created in his honor. And I'm very pleased to introduce our speaker tonight, the winner of the 2025 Patrick Supps Prize, Alyssa, if I get it right, Chair and Professor of Metaphysics in the Faculty of Philosophy, Philosophy of Science, and Religious Studies at the Ludwig-Maximilians University in Munich. She was awarded the prize for her 2021 book, The World in the Wave Function, a Metaphysics for Quantum Physics. And the award will be formally presented to Professor Ney next week at the APS November meeting in La Jolla, California. But we also wanted to share her work and news of this important prize with our friends of the APS here in Philadelphia. A metaphysician of science, Professor Ney's research focuses on questions of fundamentability, the unity of science, and the interpretation of quantum theories. As the prize committee highlighted in their selection, in the wave function, Professor Ney elegantly balances the scientific and philosophical implications of well-functioned realism, situating it in quantum mechanics within the three-dimensional world around us. Professor Ney's talk this evening, and I quote, "The metaphysics of quantum mechanics from spooky action at a distance to higher dimensions of many worlds," end of quote, wonderful title, offers several ways to reconcile physics with philosophy, grappling with long-standing debates over the fundamental meaning of quantum mechanics. Please join me in welcome Alyssa Ney.
Thank you, Richard. Thanks so much. It's really an honor to be here. And I'm really, happy to share my work today with you. So, the topic is the metaphysics of quantum mechanics. People are often wondering what that is supposed to mean. So this is my main area of research. What we're interested in, quantum foundations, this is like an interdisciplinary field where philosophers are working with physicists. What we're trying to do is understand what is the nature of reality according to quantum mechanics. And so in this field, we kind of have a division of labor. The physicists are the ones who develop these mathematical frameworks, and then they'll develop experiments to test them. If we think we've got a theory that's well tested, it's saying something true about the world, but it's formulated in a mathematical terms, we want to know, well, how do we get from this mathematically formulated theory to some clear picture of the world around us and what it's like? And that's where the philosophers come in. So what we do is try to develop different conceptual frameworks, contextualize them, try to connect this mathematical picture of reality that's so well tested with some concepts that we're more familiar with. And also as philosophers of physics, we try to provide arguments to say, maybe this is more of a right conceptual framework to use to try to interpret this theory. So what I'm going to be describing today are 3 different conceptual frameworks that we can use to try to understand the picture of the world that we're getting from our quantum theories that have been so well tested over the past 100 years now, it's been. And ultimately, I'm going to be presenting a series of theories in such a way to lead you to my preferred interpretation, which is the many worlds interpretation. But really, I mean, what I want to do here in a lecture like this is just give you more of a menu. So you're going to have several options. I'll start by just presenting what we're supposed to be knowing already on the basis of physics and what's been very well established, tested, Nobel Prizes have already been awarded. And then we'll get to the metaphysical interpretation from that. You might not want to come with me all the way to the many worlds interpretation, but I mean, you're free to get off the train at any stop along the way. Okay, so yeah, we're looking for the nature of the world according to quantum mechanics. And one of the most intriguing clues is really coming from this phenomenon of quantum entanglement. So as I mentioned, quantum mechanics was invented 100 years ago in 1925 by Schrödinger. But it was 10 years later that we really started to get a handle on this phenomenon that Schrödinger called, well, he called it Verschränkung, but what we call today entanglement, quantum entanglement. So Schrödinger called quantum entanglement the characteristic feature of quantum mechanics. But it was really I think we got the best conceptual handle on it the same year in this very famous paper that was written by Albert Einstein and his collaborators, Boris Podolsky and Nathan Rosen. I don't know if you could see this little note here. There is no picture of the 3 of them all together. So I had ChatGPT generate an image of the 3 of them and I asked what would they have looked like in 1935. So I don't know if they did such a good job with Einstein. But in any case, in this paper, actually what Einstein, Podolsky, and Rosen were trying to argue, they weren't really just trying to get a handle on entanglement. What they were trying to argue was that quantum mechanics was actually an incomplete theory. It couldn't give us a complete picture of the nature of reality. But the way that they argued this was they were showing if it was really the case that quantum mechanics was right, then you would have these systems that were entangled with each other, and this would lead to all kinds of really unintuitive consequences that didn't make sense. So if we're really going to get a complete picture of the world, if quantum mechanics is going to be part of the story, it's got to be supplemented with something else. So let me explain a little bit how this argument goes, and then we'll get a better handle on what entanglement is, and then we can move on to trying to interpret it. So when you're talking about entanglement, the core idea is you can create collections of systems, so collections of particles, for example, that have very stable, strong correlations between them. So you have a system of particles, and you're going to find them having the same value of some quantity 100% of the time. Or you have a pair of particles, and they're going to have opposite values of this quantity 100% of the time. Or they're going to have the same values of a quantity 30% of the time, 60% of the time, and so on. There are these very precise mathematical relationships between the values of these different quantities, and these will persist over time. So you can have these systems, they're created in an entangled state, you can separate them, and you're still going to continue to have these correlations persisting. For example, in quantum mechanics, one of the fundamental features that we associated with particles or atoms or molecules is spin. You can think about spin as if you like, you could think of it as an angular momentum that particles have. I mean, it's very controversial. Philosophers of physics like to debate whether anything is in fact really spinning when we talk about particles having spin. But physicists are able to create pairs of particles in entangled spin states. And so the simplest such entangled spin state, this is one I'll be talking about a lot in this talk, is called the spin singlet state. So in this case, you have a pair of particles, and on their own, so particles can always spin in two directions. So there are two definite spin states. We call them spin up and spin down, but you could think of it as just like different ways of rotating clockwise or counterclockwise along some axis. So in one very simple entangled spin state that we can create are ones where for any individual particle, there is no definite fact about which direction they're spinning, whether they're up or down. So we can take this particle over here, well, they get created together. If you measure this particle by itself, there's a 50% chance you'll find it spin up. There's a 50% chance you'll find it spin down. It's random. Same thing for the other one. On its own, if it's measured, 50% up, 50% down. But if they're created in one of these entangled states, there will be a 100% chance that if you find one spin up, the other one will be spin down. And if you measure the first one, and it's found to have spin down, 100% chance it'll have spin up. And this is the kind of thing that Einstein was really concerned about, that it didn't really make sense. He was asking, how is it the case if each of these is totally random, why is it the case when you measure them both, they're always able to correlate? I mean, just to kind of convey how strange this is, think about coins and flipping coins. So you have two coins, and you're flipping them, and you say, no, ahead of time, there's no determinate fact about this one. It's not weighted in any way. It's not more likely to land heads or tails. It's completely fair coin, 50-50. And same thing for the other one. But every time you flip the pair, they're opposite. One's head and the other tails. You would say, what's going on? This doesn't make any sense. How do they know? This one now is tails, so this one's heads. How are they maintaining this correlation? So what Einstein, Podolsky, and Rosen argued in this paper in 1935 was what you would want to say. They didn't use the example of spin. They used a different example of position and momentum in that paper. What you would want to say in a case like this, if you're flipping these coins, you'd have to say, look, don't tell me in the first place that there was a 50-50 chance that they would land heads or tails. It must be the case, if you get this kind of stable correlation, that it was already the case that this one was going to be heads, or there was something in it that was explaining why it's heads, and there must be some explanation for why this is tails. It can't be just random every time and you get this correlation. And so that's why they argued quantum mechanics has to be supplemented with something. If quantum mechanics is really saying, for example, for our entangled particles in the spin state, that it really is random whether you're going to get spin up or spin down on a measurement, but they're always correlated, then quantum mechanics must be leaving something out. There must be some pre-existing fact about the states of these particles that's explaining why they're always able to match up. Each one, when they're created, must have been created together, one with one value, the other with the opposite. So this is a kind of state of affairs in 1935. Many people didn't buy this argument. They said, well, quantum mechanics, that's what quantum mechanics predicts. This is what we have to believe. But one big step was made 30 years later, in 1964, by the Irish physicist John Bell, who said, actually, there's something that we can test here, because it turns out what quantum mechanics predicts, if we really understand entanglement, the kind of correlations that would have to be maintained by particles that are in an entangled state are so sophisticated and so complex that they actually couldn't be explained in terms of the pre-existing values of any particles. And so if quantum mechanics, the predictions are right, and particles that are created in entangled states like this entangled spin state, really can maintain these correlations over time, then that means that, well, Einstein was just wrong, because there's no way to set these pre-existing values to capture all of these correlations. So finally, it took a while for Bell's proof of this fact to be recognized, for people to test it. Finally, in 1972, the physicist John Clauser tested it, and he showed that, yeah, in fact, we do see these correlations that are predicted by quantum mechanics. And eventually, I mean, there were still loopholes in that experiment, the way that it was carried out by Clauser. So these experiments had to continue. I mean, there have been so many Bell tests, we call them now. In the meantime, most famously in the 1980s by the French physicist Alain Aspect, and then by Anton Zeilinger in Austria. This has been, eventually we have the Nobel Prize awarded in 2023 for the tests of Bell correlations. But it really looks like quantum entanglement is a real phenomenon. It's been extremely well confirmed. And even if there are some kind of additional, we call them hidden variables, that give you intrinsic states of particles and other quantum systems, they're not sufficient, as Bell proved, to explain these correlations that we have in cases of quantum entanglement. And so what I want to do, what we're going to be doing, is talking about, okay, we've got these correlations. That's what it means to say there's quantum entanglement. But how do we explain them? What could those be suggesting about the nature of our world? So they're suggesting something. It's going to be, I think, the next generation of physicists that are going to finally, let's hope, kind of get a handle on that. What is the right way to understand what quantum mechanics is telling us, what quantum entanglement is telling us, and then use that to generate new physics. But what we're trying to do now in the field is try to fight our way, through all of these different interpretations and figure out what that means. So I think it'll be easier to get a handle on these different interpretations if I just flesh out the case that I've just been talking about in a little more detail. I mean, it's a very simple kind of case, but it's one that we're able to test a lot. It's also a kind of easier way to think through. But I just want to emphasize, right, quantum entanglement is like extremely important phenomenon today. It's a basis for quantum computing, right, is that we're going to be creating very complex systems in entangled states. And so whatever we're going to say about this simple case is really what we're going to be dealing with when we have quantum technologies all around us, possibly in the next decade, who knows. Okay, so the case that I've been talking about here is this. This is what's called the spin singlet state. It's like the simplest kind of entangled state. And this is the case, we've been using since 1951 to discuss these cases. So I've written here a Greek letter psi. That's a wave function. So that's, for any system, we associate with it a wave function, and that tells us a quantum state. What we're able to do, there's a rule in quantum mechanics called the Born rule, which allows us to connect states like this with probabilities for measurement results. And essentially, the way that the Born rule would work in a state like this is you have these kind of coefficients here, 1 over square root of 2, 1 over square root of 2. And what these coefficients tell us is the probability that you're going to find the system in one or another of these states. So to read this, I was talking about having two particles that are entangled with respect to their spin. They could be spin up, they could be spin down. I've labeled these particles here as particle A and particle B. That's handy because we're going to talk about experiments done by two scientists, Alice and Bob, in their lab. So particle A is a particle that's going to be sent to Alice in her lab, who's going to measure the spin of that particle. And particle B is this particle that's going to be sent to Bob in his lab. And what we can see is if a system is created in this entangled state, in the spin singlet state, there is a 50% chance that if Alice were to measure her particle, she would find it to have spin up, and a 50% chance she'll find it to have spin down. So that's just what we were talking about. It's completely random. It's like a fair coin, whether she's going to get up or she's going to get down. How these measurements work is pretty simple. So we use this setup. It's called a Stern-Gerlach device. It's just a pair of magnets. And so if you have a particle, you send it through these magnets, it's going to get deflected up or down based on its magnetic moment, based on its spin. And so we'll say if Alice measures her particle, sends it through her Stern-Gerlach magnets, it gets deflected up, we'll say that means it turned out it had spin up, 50% chance that happens. And if it gets deflected down, it has spin down. But we can see there's more information on this quantum state. It says actually there are only two possibilities for the combined measurements that both Alice and Bob might do if they both measure their particles. And there's a 50% chance that Alice and Bob will find their particles in these states. Alice finds up, Bob finds down, and a 50% chance Alice finds down, Bob finds up. And so this is a kind of, it's very surprising what happens. Alice and Bob's lab can be separated extremely far, but we know with certainty, and again, this has been very well tested, that if Alice measures her particle and it gets deflected up and she sees a hit on the screen here saying, okay, I found it a spin-up particle, there's a 100% chance that Bob's particle is going to be found down at the bottom of the screen. Okay, so that's what quantum entangle, that's what it shows. And so we've done these experiments again. It's happened very many times. There's actually, as I mentioned, what Bell was showing was these kind of correlations can get pretty complicated. So actually, I've just drawn the most simple setup here where Alice and Bob's magnets are aligned in the same way, but they could be aligned differently. We'll get different kinds of very stable correlations for the two particles. And now the question is, how is this happening? How are these particles able to maintain these correlations? So again, it's completely random, according to quantum mechanics, whether or not Alice is going to find up or down. But somehow, whenever she finds up, 100% chance Bob finds down. So this is our question. Something funny is going on. Reality is different than we thought. And now we want to know, how is it different? Okay, so we're going to find, well, let me just summarize where we are. Schrödinger called entanglement the characteristic feature of quantum mechanics. Physicists, experimental physicists, have now proven it to be real in the stable correlations we find, even when these labs are separated over extremely great distances. And our question is, how should we understand this metaphysically? In other words, what is it saying about the nature of our world? Something surprising, something when we understand it, we're going to want to manipulate, right, and take control of it. But what is it? That's what we're trying to find out. Okay, so the first answer is just the most flat-footed answer. They're communicating, right? Einstein called this spooky action at a distance. In a 1947 letter he wrote to the physicist Max Born, the same Born that had the Born rule that tells us what probabilities we should expect from our measurements. So the idea is, yeah, somehow, so I tell you, I've got two random coins, but somehow, every time this one is heads, this one is tails. The answer is they're communicating instantaneously. Somehow, when this coin lands heads, it sends a signal over to this other coin. And so the coin knows, oh, I better be tails. This is, of course, a puzzling phenomenon. And it's not surprising that Einstein wasn't happy with this answer and called it spooky action at distance because it looks like it's conflicting with his other extremely well-established physical theory, Einstein's theory of special relativity from 1905. So one consequence of relativity is that no signal can travel faster than the speed of light. So you can't have instantaneous, you can't have action at a distance. So if you want to answer the question of what could this be, how could we have these correlations maintained by saying somehow when Alice's particle hits the screen on the top and says, I'm up, it's instantaneously communicating with Bob's particle to say, and you better be down to maintain these correlations, then you're postulating something that violates the special theory of relativity because you have a signal traveling faster than the speed of light. At the same time, this is a consequence that I'll say many philosophers of physics and many physicists themselves say we just have to accept. This is something we're learning from quantum mechanics. It's telling us that actually you can have faster than light influence in some cases. And if you're interested in this point of view, a really wonderful book. Yeah, it gets pretty hairy, but it's in its third edition now, which is very unusual for a philosophy book. is Tim Maudlin's Quantum Non-locality and Relativity. So Tim Maudlin's a philosopher of physics at NYU. And he argues for this point of view. He says, nope, we're learning from these tests of quantum entanglement that you can have causal influences that travel faster than the speed of light in violation of relativity. But some of us have been interested to explore alternatives. So we want to accept the fact, like we can't deny what these experiments have shown us over and over again. There are correlations that are able to be maintained over great distances. They certainly do seem to suggest that systems can affect each other at greater than light speeds. But what we want to explore, what I've wanted to explore in my work, is maybe there's a deeper truth about the nature of reality that's being revealed by these correlations, and that's able to explain it. And then the thought would be, once we learn this deeper truth, we won't anymore find a conflict between these two pillars of modern physics, quantum mechanics and special relativity, because it's not going to be the case in order to maintain these correlations that we find in entanglement that anything is traveling faster than the speed of light. That's just not how the correlations are maintained. So this brings us to the second answer. The second answer is higher dimensions. So this was a proposal that, it's what I was developing my book, The World and the Wave Function. It was one that's been developed, let me back up even more. So this is a kind of interpretation of quantum mechanics that really has its roots in Schrodinger's understanding of quantum mechanics from all the way back in 1926. So in 1926, Schrodinger proposed his famous wave equation. And the whole motivation for it was Heisenberg and his collaborators Born and Jordan had given this one interpretation of quantum mechanics that we call now matrix mechanics. It was very unintuitive. And so what Schrodinger wanted to do was to give a kind of formulation of quantum mechanics that had an intuitive interpretation that we could make sense of and wrap our head around. So the equation that he provided was a wave equation. So what it said is fundamentally reality is this wave that's evolving over time. Now, unfortunately, what happened was that over the next decade, physicists started to notice that there was this phenomenon, quantum entanglement. And if you have entangled systems, then the wave function that represents them can't be represented in our ordinary three-dimensional space, but it actually had to be represented in a much higher dimensional space, the space we call now configuration space. And so Schrodinger said, okay, that doesn't make any sense. I'm going to get rid of it. I'm not going to adopt that anymore. But it is something that kind of came back in the 1990s. And so the philosopher of physics at Columbia, David Albert, has been defending this point of view for a while. He's still defending it. So I found this very inspiring, especially because I thought that this might give us a way to make sense of spooky action at a distance. So that's why I decided to write a book about this. And a nearby proposal, it's not exactly the same one, has been defended by Sean Carroll in his work. So in Sean Carroll, he's a physicist at Johns Hopkins, he argues that we should also think that the fundamental reality of quantum mechanics is high dimensional, but he's going to develop that in a different way. He would say not reality as a wave function in a configuration space. He would say reality as a vector in a Hilbert space. I'm not going to develop this point of view here. If you're interested, I'm happy to talk about it in the Q&A. I'm just going to kind of proceed with this other higher dimensional interpretation that it's more finding its inspiration in Schrodinger's original wave formulation. So the basic idea here, the reason why we would want to defend, or why I would want to defend a high dimensional picture, is the thought is we can somehow see these correlations in three-dimensional space, not as really revealing some kind of instantaneous causal influence between systems across space, but instead as manifestations of a reality that doesn't have any action at distance in higher dimensions. So this is really hokey, but I have a prop here to kind of intuitively get the idea here. I don't know if you can see these two dots that I wrote. So here's the idea. So, you can think about these as Alice and Bob's lab. separated at a distance. So here we've got a two-dimensional, right? It's just a piece of paper. And so in this 2 dimensions, Alice and Bob's labs are separated by some distance. We haven't taken into account the 3rd dimension here, right? But if we put this in, if we recognize the 3rd dimension, we might say, yes, even though in this 2-dimensional plane, it is the case that they're separated, if I can fold this, in the 3rd dimension, they're still separated in these 2 dimensions, but once we recognize this higher dimension, we can see they're actually right next to each other in that higher dimension. So this idea is familiar we have physical theories already, like string theory, that postulate more dimensions than we're used to already. This is not exactly the picture that David Albert and that I've been developing. The difference here is that, again, the basic idea is the same, is you say that things that actually seem to be at different locations and separated in one kind of dimensional reality are actually connected in a higher dimensional reality. That is the idea. But in this kind of higher dimensional wave function picture, there are none of these 3 dimensions. It's not like in this picture or in string theory where you have our ordinary 3 dimensions or 4-dimensional space-time, and then you add additional dimensions. Instead, the idea here is that we have a completely different set of reality. And so again, the idea is fundamentally the world is a wave function in a high-dimensional space, we say, with a structure of a configuration space. I'm going to explain in a minute now what I mean by configuration space, because I think it's helpful to get a sense and wrap our heads around what this proposal is. But I just want to say, just quickly, because people always complain about this, I'm using the term wave function just because that's standardly how it's often, this idea is promoted. But you shouldn't be thinking, because I say function, I'm talking about a mathematical object. The view is that the world is fundamentally this wave evolving in a high-dimensional space. And we call it the wave function just because the correct representation of it is given by that wave function, that psi that we use to represent quantum states. Okay, so let me talk a little bit about what this higher dimensional space is. So I said it's configuration space, or it has the structure of a configuration space. Configuration space isn't a concept that was introduced only for quantum mechanics. The concept of a configuration space actually was introduced in the early 19th century to make sense of classical mechanics and classical states. So it was used by Lagrange and Hamilton. It's at that time when we're talking about classical physics, by which I just mean non-quantum physics, so like Newtonian physics, we're working with very different kinds of systems. One salient distinction between classical physics and quantum physics is in classical physics, particles can always be said to have definite locations. So what configuration space does, it allows us to have a very simple representation of the positions of a system that may contain very many particles. So here's the basic idea. We're very familiar, right, from when we were in school with how to represent the locations of particles using the Cartesian coordinate system, right? So if say you have 2 particles in your system and you want to represent where they are, you'll use these 3 Cartesian coordinates, x, y, z, and then with each of these particles, you'll associate 3 numbers, right? So you associate 3 numbers with this particle, and that you say is its x, y, and z coordinates. And then you associate 3 numbers with this particle, and that's its x, y, and z coordinates, and then you're done. You've captured all the information you need to say exactly where these particles are. In configuration space, we basically do the same thing, except we're only needing 1 point because we're going to use a higher dimensional space. In general, for configuration space, the space is going to be 3n dimensional, where n is the number of particles in your system. So in this example, I just have 2 particles, so we just need a 3 times 2, 6-dimensional configuration space. Again, you need the same amount of information as you did here. So here we needed 6 numbers, 3 to get these x, y, z coordinates, 3 to get these x, y, z coordinates. Again, we're just going to need 6 numbers, but we only have 1 particle, but there's 6 dimensions. We can move back and forth very easily between these two representations, though, because we can just say the first three numbers correspond to the x, y, and z coordinates for the first particle here. The next three dimensions correspond to the x, y, and z coordinates for this particle here. So that's configuration space. And it's a very handy mathematical tool in classical physics, because you can think, especially if you're dealing with a huge system of 1,000 particles, instead of having to keep track of all of these lines, you can represent the evolution of the states of all of these 1,000 particles by just one line through this higher dimensional configuration space. Okay, so that's basically the space. Now the difference is if it was the case in quantum mechanics that particles always had definite locations, we'd just be dealing with this picture. We could say the world is just this point in this higher dimensional space, because all of the information about where all the particles are is represented by just this one point. But of course, in quantum mechanics, we know systems generally don't have determinate locations. So you have to think of them as more like, some people like to say, well, probability waves. That is controversial. I shouldn't have even said that. But the idea is you can think about them as smeared out over this space. And so fundamentally, here's the idea. The world is fundamentally a wave function in a high-dimensional space. That means it's this thing that, like a wave, has different peaks and valleys at different points over the space. We call the values of how high it's peaked at a point or low it's peaked the amplitudes of the wave function. And so for a wave function like this, if we had a very a high amplitude wave function here, so the wave function was very peaked at that point in space, what that would mean is it's very, very likely that our particles would all be found at the locations corresponding to that point, right? So particle 1 would have x1, x1, y1, z1 as its coordinates. Particle 2 would have the next three numbers as its coordinates, and so on for all the particles in our system. Okay, so that's the picture. And the key point, the way that this is going to get you some kind of avoidance of action at a distance, is you can see at each point in the high-dimensional configuration space, each point corresponds to all of the particles in our system, right? So let me go back here, right? So here, what we were saying is this one point will tell you where all of these particles are. So information about all of these particles is contained in each point in the high-dimensional space. So the information about Alice's lab and Bob's lab, Alice's particles, Alice, Bob, each contained in each point in that high-dimensional space. So to summarize what's going on in here in this picture, what we will say is, in the three-dimensional way that we standardly represent the world, it does look like Alice is over here and Bob is over here. But in the high-dimensional image, really, these things are not separated. Okay. So the picture that we're understanding is something like this. So there are some people who would adopt this picture and say something like, there really only is a fundamental high-dimensional configuration space. That's the whole reality. More likely, when people are developing this point of view, what they'll say is, it's not that there isn't these three dimensions. The three dimensions or four-dimensional space-time are real, it's just they're not fundamental. And so what we have is a fundamental reality as this high-dimensional thing, where it's local in the sense that just means all causal interaction is local. There's no action at a distance. But somehow the behavior of this wave function over time gives rise to the picture in three dimensions where things seem to be interacting instantaneously across spatial distances. Okay, so that's the high-dimensional picture. Now, I wrote this book. It was published in 2021. I've moved on. I'm not satisfied with this picture. And let me tell you why. The reason is, although this is a very intriguing idea, and so it's attractive in the sense that if you were worried somehow it didn't make sense that you could have action at a distance, this at least does give you a fundamental picture of reality in which you just have this smooth wave function evolving. There's no non-locality in the fundamental picture. But even if it is the case that in the fundamental picture of reality here, there's no action at distance, this picture really does nothing to remove the kinds of appearance of a violation of special relativity that we see in the low-dimensional picture. You still have these surprising correlations in space-time in the low dimensions, and those conflict with what relativity says, that there shouldn't be any such correlation. There shouldn't be any influences in low dimensions. So for that reason, I was interested in seeing, well, is there a way, I mean, maybe this is right, maybe the world is fundamentally this high-dimensional wave function evolving over time, but I was interested to see, is there any way that we can give a picture of the world according to quantum mechanics that is local in low dimensions also, that's local in the four-dimensional space-time in which we seem to live. And that brings us to the many worlds interpretation. Okay, so today the answer I prefer to, when, if you were to ask me, like, what is the reality suggested by quantum mechanics? So I would say, I don't know. We're just kind of really starting. We've just not had clues for that long. But the picture that I prefer is the many worlds interpretation. So let me give a little bit of background about this, and then we'll get to how it avoids action at a distance. And if there's time, maybe I'll talk about why people are worried about the many worlds interpretation and why those arguments aren't very good, and they shouldn't be worried. So the many worlds interpretation was originally proposed in the 1950s in a dissertation by a PhD student at Princeton called Hugh Everett. He was a student at John Wheeler's. And he proposed this as the theory of the universal wave function. And it was in Everett's view that he wanted to argue against the standard interpretations of quantum mechanics were popular at the time, honestly, that are still popular today, that involved collapse of the wave function or the Copenhagen interpretation. And this was the theory he proposed. Mainly, he didn't propose it because he wanted to avoid action at distance. I mean, I say mainly, I mean, he barely mentions this at all in his dissertation. There's one little reference to EPR, the Einstein-Podolsky-Rosen paper that I was mentioning earlier, and says, if you adopt my scheme, then you can avoid these paradoxes that EPR were talking about. But that's really not, I mean, he's really developing it for other reasons. By the 1970s, this proposal, this theory of the universal wave function, was recognized to commit you to, it looked like parallel universes. And it was popularized by the University of Texas physicist Bryce DeWitt and became the many worlds interpretation of quantum mechanics. Now, I want to just emphasize, if you adopt the many worlds interpretation, it's possible to combine that with a higher dimensional picture. So actually that I had mentioned Sean Carroll earlier. Sean actually does develop both of these ideas. So he likes the many worlds interpretation, but also thinks the fundamental reality given by the many worlds interpretation is a higher dimensional reality. But I just want to emphasize, most people who like the many worlds interpretation don't do that. So you don't have to put it together with higher dimensions. You can just, and honestly, this is the way that I propose that we understand it. So the idea is going to be, if you understand the quantum mechanics in the way that the many worlds interpretation says you do, you don't have any spooky action at a distance. It's completely local. And so if you're interested in more, I'm going to argue this extremely quickly here in the time I have, but if you're interested, I do have a paper that you can find on my website that's called The Argument from Locality for Many Worlds Quantum Mechanics. Yeah, I wrote this a few years ago, but it takes a very long time for journals to actually publish your paper in philosophy, so it's been forthcoming forever here, but it is linked to my website. And I've also just put together a collection of essays where many kind of philosophers and physicists who are excited about the many worlds interpretation are arguing why this is a local theory. So this will be coming out with Oxford University Press next year. So to see how the many worlds interpretation avoids spooky action at distance, I just want to back up a little bit and say in a little more detail how you understand these correlations according to the standard textbook formulation of quantum mechanics. So according to the standard, and then we'll contrast this with the many worlds interpretation. So according to the standard textbook interpretation of quantum mechanics, what happens is you can have a system that's described by a wave function like this, that's smeared out over different possibilities for measurement results. But once an observer conducts a measurement, so for example, Alice comes and measures her particle, what happens is the wave function undergoes a collapse. And the way to understand that is we can just think of, we had this wave function, it had two possibilities, right? Alice could find up or Alice could find down. Bob could find down, Bob could find up. As soon as one of them does their measurement, whichever one happens first, one of these terms is going to disappear. And so if we see what I've drawn here, Alice sends her particle through her Stern-Gerlach device, it hits a detection screen here, that means the particle was found up, that means this wave function collapsed and this term goes away. And all you have left is this term. And so what you have on the standard textbook interpretation of quantum mechanics, it looks like a spooky action at a distance. Alice's measurement has collapsed the wave function, and that immediately causes Bob's particle to collapse. It's now no longer smeared out over these two possibilities of being up or being down. Only this term remains. It's become definitely up. No, down. So there it goes. The main thing that Everett wanted to propose was, let's get rid of this collapse. If we get rid of collapse, then, well, a lot of problems are solved. But let's just talk about the spooky action at a distance here. So if we have the many worlds interpretation, what we say is actually, what we have here is a description of two systems. We've got this particle that's up, we've got this particle that's down. And now what happens when the system is sent through Alice's lab? Well, this part is going to go up, it's up. This part is going to go down, it's down. And as the particle becomes entangled with Alice's lab, with Alice's magnets, with a detection screen, and eventually when Alice looks and sees where the particle is hit, the particle becomes entangled with Alice, the universe branches. And you wind up having not one, but you wind up with two pairs of magnets, right? One that was deflecting her particle up, one that was deflecting it down. Two detection screens, one where this is hit here, one where this is here, and two Alices, one who sees up and one who sees down. And so now if you want to ask, how is it the case that Bob's particle knows to go down when hers went up? The answer is Bob's particle, again, there are two Bob's particles. One is going to go down, this one. One is going to go up, this one. And so it doesn't need to, it's not like on the first theory where you say, look, if that one's up, that one better not be up too, it's got to be down. No, both particles can just evolve naturally according to their wave equation. They're both going to be up, they're both going to be down, and so you don't need to have any kind of communication between the two to make sure that happens. The correlations are maintained. That's the idea. Okay, so now let me wrap up. I'm sure there's questions, but let me just kind of wrap up where we are so far. So we've seen three ways of making sense of quantum entanglement. The first is you would just say, there's spooky action at distance. It turns out the way that the particles in an entangled state are able to maintain these stable correlations over time is because they're able to instantaneously communicate with each other somehow. And yes, there's a violation of relativity, but that's what we have to accept. The second possibility is you say these correlations that are able to be maintained over great distances are being sustained by this higher dimensional reality in which those things are not actually separated in space at all, but at the same location. And then the third option is that you say, well, we have the many worlds theory. So actually, we don't need to have any kind of spookiness in the three-dimensional picture at all. It's just the natural evolution of the wave function ensures that you have all possibilities in all cases. And so yes, there's a possibility where Alice is seeing up and Bob's seeing down, and a possibility where the opposite occurs. I want to say, at this point, you can ask, well, test it. Why can we propose a test and see who's right here? Is there really spooky action at distance, or hidden dimensions, or many worlds, parallel universes? The answer is no. There is no experimental test that can decide between these. And the reason is because these are all metaphysical interpretations that were cooked up to make sense of what we know from the experiments. So they're all compatible with quantum mechanics. They're all compatible with any test that you want to do. At the same time, I don't think that this is just a matter of I like this and I like that. Really, there is a good reason to decide between these, and that's because the many worlds interpretation is the only interpretation that's not in conflict with this other part of physics that's also extremely well confirmed, which is special relativity. And so even though you can't do it, I can't do it, propose a test and say, now we've proven many worlds, I can say, unlike the other interpretations, it's compatible with relativity. And so that is a scientific reason to support it. Now, I think there's like 1 minute left, so maybe I won't have that much time to go into this, but I just want to acknowledge, you could say, oh, well, if it's that easy and it's just a scientific fact that this is the only interpretation that's compatible with relativity, why doesn't everybody accept it? Well, there are two main reasons that people have been wanting to stay away from the many worlds interpretation. So the first reason is like a little more technical. This is what philosophers of physics usually complain about. So yeah, most philosophers of physics I know don't like the many worlds interpretation. And what they'll complain about is they'll say, yeah, but you told me that quantum mechanics is a probabilistic theory, right? What about the Born rule? You had said, if I have a wave function, if I have a quantum state, then there's this rule, the Born rule, that tells me in a state like that, there's a certain probability we'll see this, a certain probability Alice will see that. What happened to those probabilities? Now you're telling me definitely everything's going to happen all the time. So that's a challenge. If you adopt the many worlds interpretation, you have to say, what do those probabilities, how are their probabilities here? And then the second objection is this problem of ontological bloat. So this is really why John Wheeler, although at first he was really intrigued by his student Everett's interpretation, his theory of universal wave function, ultimately said, I don't buy this, because I don't buy that the universe is always splitting into all of these many me's and many you's. That's just too many. Occam's razor tells us you should prefer theories that postulate fewer entities. Okay. There are reasons to think that those arguments are too quick, so I'll just mention in the philosophy of physics there is a very active research program. There are many different ways to understand how there are actually probabilities in the many worlds interpretation. I've just kind of put a few of these proposals and names of them up. I won't have time to talk about that, but I just do want to say something about this. Are there too many me's, and isn't that a reason to reject the many worlds interpretation? I don't think actually this is a good reason to reject the many worlds interpretation. And the reason is because I think we have to be careful about how we use Occam's razor to choose between theories. So generally when, there are many ways that you can use Occam's razor and say, I don't want this theory because it postulates too many entities. But the good way, so I'll just make one of these distinctions and then I'll leave the other if it wants to come up in the Q&A. Generally, when a physicist wants to say, I prefer this theory because it postulates fewer entities, what they mean is not that it postulates fewer entities. What they mean is it postulates fewer kind of entities. So if it turns out as a consequence of a theory, there are like an infinite number of electrons, that's not going to count against the theory. Maybe there just are infinite number of electrons. What makes a standard model of particle physics a good theory is not that it has fewer individual particles, it's that it postulates fewer kinds of particles. And in the case of many worlds theory, the worry isn't that there is going to be too many different additional kinds of things. It's all the same kind of thing. It's just more of them. So it's like complaining about the standard model that there are too many individual electrons. So that's why I don't think this is a good argument, one reason. But ultimately, I think there is something to this concern with the many worlds interpretation. But I think the real problem isn't with too many yous and too many me's and too many parallel universes, is that it violates Occam's razor. I think it's just creepy. We don't want any other us's out there. Many of us do. Okay, so in conclusion, I think we know we have extremely good reason to believe in quantum entanglement. It's a real feature of the world. These stable correlations persist. They persist over great distances. This is what the work of Clauser and Spey and Seilinger have shown to us, and so many others. But what these correlations imply about the nature of reality, about the metaphysics, is still something that's up for debate. And this is one of the main challenges in philosophy of physics. But I want to argue the many worlds interpretation is the most attractive way of understanding it to date, because it's the only interpretation that is compatible with relativity. And for this reason, and this is, I know there are historians of physics here, so I'm not a historian of physics, so I can make dodgy historical claims, a philosopher, but I think that this is a reason that even Einstein might have preferred it. I mean, that is extremely controversial thing to say, but Einstein died in 1955. The many worlds theory, Everett's dissertation was published in 1957. The tests of quantum entanglement were much later, so yeah, it's an interesting question what Einstein would have preferred. But anyway, thank you very much.
We can have a Q&A. And
I'm here, I see you.
there's a microphone, so before you start speaking, make sure you have a microphone.
I do, I think. Is it on? Great. Thank you very much. I have a question. Now, I know this discussion is about entanglement, but to extrapolate, would these alternative explanations overcome the theory of collapse? Explain the Heisenberg uncertainty principle by observing you are selecting one of many possibilities in the multiverse of position and momentum? Am I correct in that interpretation?
Yeah, everything has to be compatible with Heisenberg uncertainty principle. So that's just from the start, yes.
Okay.
So there's no, whichever interpretation we're going to prefer, that's a fact. I mean, it's a simple mathematical, it's really a mathematical fact about quantum states. So if they're smeared out in position space, they're going to be not so smeared out in momentum space. And so that's just going to have to be a consequence of any of these interpretations, 100%.
Okay, thank you.
Hi, just simple noob question. For the many worlds interpretation, are the many worlds insular?
What do you mean?
At the moment that the worlds branch,
Yeah.
do they separate in a way where communication between them is no longer possible?
Perfect.
Or are they overlapping?
Yes, that's so important. So I wanted to get to, to talk about so many different interpretations that I didn't mention this, but it's crucial. It's very important. So what happens when, and this isn't something that Everett had. So when Everett developed his theory of the universal wave function, he didn't have an account of, okay, so suppose Alice does her measurement. I mean, forget about Bob for a second. Alice does her measurement. I said there are two particles, and then when the particle that's in the superposition of being up and down interacts with Alice, or the particle interacts with the detection screen, and then Alice interacts with the detection screen by looking at it, she becomes entangled, and now she's seeing this and she's seeing that. But it doesn't seem to her that she's seeing this and she's seeing that. So how is that happening? That wasn't really understood until the 90s. So it wasn't really understood until 40 years later, where we've had in quantum information theory, not just a better understanding of entanglement, but also of some phenomenon called decoherence. And so this was the physicist Zurich, also a philosopher of physics, Simon Saunders, did a lot to help us understand better decoherence and the important role it plays in the many worlds interpretation. And so it's not, and to answer your question, it's not like sharp and boundary, like causal boundary between these different universes, these different Alices. But what happens is very quickly the quantum state evolves in such a way that any kind of branch in which Alice would be able to interact with these other parts goes quickly to zero, or almost to zero. And so that's why, a question that you could have asked is like, well, why, Alice is only going to be able, if she calls Bob on the phone and says, what did you see? We know Bob's going to say, I saw down. If she says up, she says down. So what that means is Alice is somehow, this Alice that sees this is not able to see this Alice, but she's also not able to see this Bob. And so that's, if you want to say insular, the many worlds are, for the most part, causally disconnected from each other. And that was something, that it wasn't really understood why that was just going to be a consequence of quantum mechanics. It didn't have to be put in ad hoc, but it was just a consequence of how quantum states evolve when they're interacting with an environment. Yeah.
Can I go? Yeah. Well, my turn? Yeah. Sorry. I have loved this. Thank you so much. You must be a blast at dinner parties. But my question is, I'm stuck on the spooky action at a distance.
Okay, yeah.
Did Einstein just go, I'm going to table that because my life's over. I'm going to pass the baton, let somebody else figure that out. Like, that's a bizarre reference for a man who was so particular with details. Did that strike you that way, or how do you perceive his reference of that?
Yeah, I mean, I think that I don't really know. I mean, I think that now we've gotten used to quantum entanglement a little bit, and so we're used to the fact that, or at least the way I grew up reading all of these popular, physics books about quantum mechanics and trying to understand. I'm used to like there being all of these quantum mechanics being weird, and there being it's going to say something really strange. But yeah, these Bell tests happen, I mean, the first one in the 70s already. So we've kind of had quantum entanglement for a while around us. So I don't know, it's hard for me to know. In 1947, quantum mechanics is coming, and it's really overturning a lot of, especially when Schrödinger and Einstein were really wrapping their heads around entanglement, what that was saying. And yeah, I try to give the case of the coin flips, because it would just be like, you're telling me there's nothing about these coins that's already said that they're opposite, but somehow they're just going to keep matching. You would say, no, this is wrong. So I don't know, I think it was a reasonable, I meant to say this actually, and I didn't, so thank you. When I presented the EPR argument, I mean, I think it was a completely reasonable to say, quantum mechanics is leaving something out. There must be some additional fact that's explaining why you would have these correlations, if you indeed really do have them. I think that was a reasonable thought to have at the time. Yeah.
Hi. It's a three-part question, so feel free to answer as many or as few as you want. First is, are you able to speak to Gödel's views on everything that's going on, given his relationship with Einstein and the way he thought? Another one is, does loosening some of the constraints or assumptions in terms of Heisenberg uncertainty principle or the speed of light, does that allow, does that give us more wiggle room to explain what's going on? And then the third one is this just a result of having a probabilistic theory that if we had a different, more intuitive theory, things like these will go away, similar to like the epicycle stuff with the early solar system? Yeah,
okay, that's a lot. So, I mean, yeah, those are the deepest questions you could ask. So about Gödel, so are you thinking about like Gödel universes and like closed time-like curves?
No,
I mean, that was his model of general relativity?
Just the way that he was a beast with logic and he just saw things. Like, my question is like, is there any correspondence or any documentation on if Einstein spoke to him in frustration and what he would say, given his views of logic?
That's really interesting. I actually don't know about that. I mean, I think, I think that's interesting. I don't know anything about, Gödel and Einstein having conversations, like on their walks or about this kind of topic. Heisenberg uncertainty principle, I mean, I guess I don't know what to say. I mean, I want to say again, I think that this is just understood to be, and the way I understand it is, it's just a mathematical fact. So you can't really undermine the fact that when you have a system that's smeared out, or that has some kind of uncertain, or let's say that it has some kind of precision, in terms of, for example, its position, that it's going to also at the same time be smeared out in terms of its momentum. So I think, I don't know, from my perspective, what I want to do instead is say, okay, let's take that on board as a fact and now try to interpret it. The last point, yeah, so the many worlds interpretation is a completely deterministic theory. So actually many of the interpretations of quantum mechanics that are being developed now don't have collapse of the wave function anymore. And so usually we think, okay, now we have quantum mechanics, so we have indeterminism, we have really fundamental randomness and chance. In a sense, that's right. I mean, there is randomness, but it's not that if you have this interpretation or some other, that there's really no fact about the matter about what's going to happen at the next time. The chances in this theory are usually thought to be epistemic. So the way we understand probabilities is there's something that an observer, given their situation, doesn't know. And that's why we can say, for that observer, it is completely random, because they can't predict what's going to happen, or they don't know what branch of the multiverse they're in, or something like that. But yeah, I mean, we're kind of at this stage, again, where we're keeping all the options on the table, and so I think it's right to want to pursue both probabilistic and non-probabilistic options. But the many worlds theory is deterministic. It doesn't have any fundamental chances.
I'm afraid the random forces in the universe have to bring this interesting Q&A session to a close. I want to thank you so much.
Thank you.
Thank you all for coming. And before I let you go, I should note that the APS has 2 more public lectures this year, one next week in La Jolla, California. You can take a train if you can't get on the plane.
Yeah.
You can still register for it. And the final lecture will be back here in Philadelphia, December the 18th, and it will explore the newly published Encyclopedia of Philadelphia. So please keep your eye on the website and details, and you can register for that and come here in person preferably, or you also can listen online. But thank you again for a fascinating evening. And there's copies of Professor Ney's book in the back if you wish to buy it. And you could sign it, perhaps. Thank you. Thank you all for coming. Here, yeah, we can have everything.